So today we're going to be looking at the number of moles and volume, looking specifically starting with volume. So we're going to look at the relationship between volumes of gases that react with each other. And I'm not sure if we'll actually get to the ideal gas law or not, because there's a couple of things I got to talk about first, but we'll see as we go. So in the early 1800s, Gay Lussac was studying gas volume relationships when he was looking at the reaction between hydrogen and oxygen. So he observed that 2 liters of hydrogen can react with 1 liter of oxygen to form 2 liters of water vapor. There she is. Okay. Yay, everyone's here. Okay, so just purely by observation, he observed 2 liters of hydrogen react with 1 liter of oxygen to form 1 liter of water. So if we represent those with the volumes here, we can see the ratio between hydrogen to oxygen to water is 2 to 1 to 2. Okay, just said that already. So this ratio is going to apply to any proportion of volume that you use, whether it's milliliter, liter, or cubic centimeter. Gay Lussac also noticed that ratios by volume between other reactions of gases. So another example he looked at was hydrogen gas and chlorine gas to form hydrogen chloride, and that ratio was 1 to 1 to 2. So he came up with Gay Lussac's law of combining volumes of gases, which states that at constant temperature and pressure, the volumes of gaseous reactants and products can be expressed as ratios of small whole numbers. So I want you to keep that in mind. It's really important to remember this. Volumes of gaseous reactants and products expressed as ratios of small whole numbers, because we're going to combine that with ideas that Avogadro had, and we're going to come up with a way to link this back to what you learned last year as far as coefficients and balanced equations. Okay, so for now, Gay Lussac is just saying that when you look at reactants and products, their volumes can be expressed as small whole numbers. Then we get back to this guy Avogadro, the same one that came up with Avogadro's number, which was 6.022 times 10 to the power 23. But he started looking at Dalton's atomic theory. Now, one important point of Dalton's atomic theory, if you remember from last year, it was that all matter is created of small particles. These particles are indivisible. There were 5 parts, and I can't remember all of them, but 2 of the parts were incorrect. One of them is this part that's on the screen now. Atoms are indivisible. Now, we found out later after Dalton, when we started doing the experiments like the gold foil experiment and the cathode ray tube, that we found that atoms are in fact divisible because they're made of smaller parts like the electron, proton, neutron. And the second part of Dalton's theory that was wrong was that he said that atoms of the same element have the same like size and mass or something, but we also know, of course, now about isotopes. Anyway, so Dalton thought of particles of gaseous elements that they existed in the form of single atoms. So Dalton believed that one atom of one element always combines with one atom of another element to form a single particle of product. So they literally like come together to form one thing, not just one substance, but like one particle. So if we look back at Gay Lussac's results, especially if you look at water, if you have 2 volumes of hydrogen reacting with 1 volume of water to form 2 volumes of hydrogen that react with 1 volume of oxygen to form 2 volumes of water. Yeah. This is going to be a problem for Dalton. Okay, so if we say 2 to 1 to 2, it would seem that according to Dalton, that oxygen would have to divide into 2 parts in order to make Dalton's theory of atoms being indivisible in order for that to be true. So, about 8 years after Gay Lussac came up with his law of combining volumes, he found a way to explain Gay Lussac's law of combining volumes without violating Dalton's idea of indivisible atoms. So, he rejected Dalton's idea that elements are always in the form of one atom. So he reasoned that some molecules, especially when you have a gaseous element like hydrogen and oxygen, that they could be, in fact, diatomic, or they could contain more than one atom. So Avogadro's law states that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. So at the same temperature and pressure, the volume of any given gas varies directly with the number of molecules. So I just want to talk about that in terms of a mathematical equation, like what we learned about with Boyle, Charles, and Gay Lussac and their gas laws. So if we translate to a mathematical formula, we have volume varies directly with the number of molecules, which we use a lowercase n to represent the number of moles. And of course, if we want to make it an equality, we introduce k. And so then finally we get V over N equals K. Now we don't actually treat this as a separate gas law like we looked at P1V1 equals P2V2 like that. We don't actually do that with Avogadro. Instead, later on, we're going to combine Avogadro's law with the combined gas law to form one beautiful ideal gas law. But I want to look at the relationship between Gay Lussac's law of combining volumes and Avogadro's law first. So Avogadro's law also indicates that gas volume is directly proportional to the amount of gas at a given temperature and pressure. So again, we have V equals Kn. K is the constant, of course. N is the number of moles. Shoot, where is that? Oops. Where is that graphic? Okay, so I want to go back to just show you, what do you call it? Like a visual representation of what Avogadro's law means. Avogadro's law, let's go back to, where does it say? There it is. What it actually states. Equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. So that means it doesn't matter what the gas is. If there are equal volumes, they will have the same number of molecules. So we can extrapolate that and calculate how many, what the amount of gas is for a particular volume at STP. And when we do that, when we measure the amount of molecules for a particular volume at STP, we see for all three of these gases that at STP, 1 mole of gas, whether it's CO2, O2, or H2, occupies a volume of 22.4 liters, no matter what the gas is. This is a demonstration of Avogadro's law, what he was talking about. So whether you have equal volumes of gas contain the same number of molecules, or the same number of molecules of gas are going to have equal volumes, this is still a demonstration of Avogadro's law. So what we call this, what you're looking at here, that 1 mole of gas at STP occupies a volume of 22.4 liters. That is something called, where is it? So I'm trying to look at my iPad to see what slide I'm on. Here we go. That is called standard molar volume. This is going to allow you to convert between moles and liters in a conversion problem, as long as it is, I can't talk today, as long as it is at STP. You cannot use standard molar volume if it's not at STP. Okay. If we have temperatures and pressures that aren't standard, then that's when we go to the ideal gas law to use that. But I want to practice a little bit with standard molar volume. Excuse me. Ugh. All right. So Knowing the volume of a gas, you can use 1 mole per 22.4 liters as a conversion factor, which means you can find the number of moles, which also means you can find the mass. So if I give you the volume of a gas at STP and I ask you to find how many grams that is, you can now do that. And of course, you can go the other way. If I give you the mass of a gas at STP, you can find the number of moles or the volume as well. So one of the things, I guess I don't talk about it here, but I do want to mention it. If I go, because I told you to remember, nope, not that guy. Gay Lussac's law, where did he go? Here. I told you to remember this, Gay Lussac's law, expressed as ratios of small whole numbers. Now, why that's important and why it combines with Avogadro's law is that when you have a balanced equation, so we've got 2 hydrogen plus oxygen yields 2 water. Now, last year, I taught you why we balance equations is to satisfy the law of conservation of mass so that mass isn't created or destroyed. You don't lose atoms or create atoms out of nothing in an equation. So last year you were using these coefficients to represent the number of moles, but now because of Gay Lussac's law, it actually represents volume as well. And that was demonstrated by his experiments when we look at, come on. Oh, why is it so slow? Here, when we look at an equation like hydrogen and chlorine forming hydrogen chloride, we have 1 to 1 to 2. So if I were to actually write out that equation, so hydrogen gas plus chlorine gas yields hydrogen chloride gas. If I asked you to balance that, hydrogen would be 1, chlorine would be 1, and this would be 2. So last year when we used these numbers to represent moles, we now know that they can also represent volume as well. So there's a lot of ways that you can convert now using volume and Gay Lussac's law of combining volumes, Avogadro's law, so that you can convert between volume, moles, and mass. So let's do a practice problem first. We'll go over first, and then I'll have you do a couple practice on your own. So for example, wait, before I do that, does anyone have any questions? Okay, so everyone understands everything. Awesome. All right, a chemical reaction produces 0.068 moles of oxygen gas. What volumes in liters is occupied by this gas sample at STP? So the first thing we want to do is analyze the information that we're given. We're given the, why did I write molar mass? That was stupid. I'll change that later. It's not molar mass, it's just the moles. Okay, we're given the moles of oxygen, which is 0.068, and we want to know the volumes. Because it is at STP, we can use standard molar volume. Again, because it is at STP, we can use 22.4 liters per mole. So then we just plug in the numbers, and of course we cut our units and we get 1.52 liters of oxygen.